It's weird, right? Say again?
Well, you'd have, you know how near the zero there's a lot more space between them?
Here, yes, in here.
There would be a lot more numbers there, right?
So I'm saying area like if you were to try and paint this, right?
Oh, okay.
If you were trying to like paint this surface, are you going to need an infinite amount of paint or is it going to be a finite amount of paint? It turns out for some problems it would be finite, some infinite. Let me give you another problem. I trust me, I have enough time. This is just to get you thinking, all right? So don't give me an answer yet, all right? I want everyone to think about this. I want you to think of it, and then I'll ask you for your answer. We're going to take a vote. All right, this is a theoretical problem, okay? Purely theoretical. You'll know what I mean once I do the problem. Let's say that we have a container that holds exactly 1 cup, okay? 1 cup. What's a cup? 8 ounces, something like that? So this theoretical container has been measured. It's precise, exactly 1 cup, all right? So here's what I'd like to do. I'd like to come in here with a little pitcher of water. We'll do water. Normally I do beer, but it's morning. It's too early for beer, I guess. So here's a pitcher, and we're gonna pour some water in here, right? And what I'd like for you to pour in here first, all right? I'd like for you to pour into it 1/10 of a cup. Okay, pour it in. You see it there at the bottom of the cup? Yeah? Okay, now after you do that, I'd like for you to pour in 1/100th of a cup. So you poured some more in there, right? Okay, now I'd like for you to pour 1/1000th of a cup in. Now 1/10,000th of a cup in. If you could do it, theoretically, right? Theoretically, if we could do this. And I'd like for you see the pattern here? I'd like for you to continue that forever.
So it's like fun.
Well, my question, what do you think my question is?
How many pours would it take
To what?
to fill it?
Does the cup fill up? Does it overfill? Don't answer. The question to you is, if I continue this, so I pour in 1/10, here comes the water, right? Pour in 1/100th, 1/1000th, right? And I keep doing that forever. The question is, will the cup overfill? Think about it. I'll ask you for your answer. I want everyone to have a chance to think about it. Does anyone have a question about the question?
Did you say the pitcher had a cup in it as well?
No, the pitcher, don't worry about it. We have an infinite amount. We have an infinite supply of water, okay? So we're not going to run out of water. We're just going to keep doing that forever, all right? So you either think that that cup's going to overfill or you think it's not going to overfill, okay? Right? That's what you either think it is or you think it isn't. So let's take a vote. Just raise your hand. You don't have to play if you don't want to, but let's take a vote. How many of you think that if I do this continually forever, never stop, that it will overfill? Okay? How many of you think it will not? 2 knots? Okay? 3 knots? I mean, obviously I'm asking the question because there's something interesting about it, right? So for those of you who have the argument that it's going to overfill, does someone want to state your argument? Who wants to state it? Go ahead.
Just for the simple fact that we're able to keep on filling the cup to infinite amount of time. Eventually, you're going to get over the ecos.
Okay, so let me help you refine your argument. So you're telling me that this is a positive amount of something, right?
Yeah.
And this is a positive amount of something, right?
Yeah.
And this is positive. And so you keep on adding up positive numbers forever, right? You keep adding. And this is a finite container, right? 1 cup, exactly 1 cup. We're not talking about evaporation and shit like that here. We're just saying purely theoretical, right? I like that argument, right? Who's going to argue against that? Who's going to say, okay, you mean to tell me that if I take some positive amount of something, which will take up space, right? And then add to it another positive amount, that's going to take up space, that I'm going to not overfill this? I like that argument. Do you have something to add?
Having that, you also said the cup had an infinite amount of water inside.
Yeah, we're not going to ever run out of water either, so we can keep doing this. Okay, now, the people who said no, do you want to make an argument for no?
I feel like I have something in my head, but I don't know how to explain it.
You're not sure how to express it?
Yeah.
Do you, any? No? Is it just like a gut feeling?
I could argue the other way.
I mean, each
Hold on.
time that you feel it,
Okay, so these are getting smaller. We agree with that. Yeah? It is getting smaller each time. So, I mean, I agree. It is getting smaller. But it's still something, isn't it? It's still something,
If you
though.
write it out as like a decimal, it's just going to be 0.
Okay, so
That's
check
it.
this out.
It'll never reach 1 because it's just adding another.
If you take this and turn it into a math problem, here's what you're doing, right?
You'll never hit 2 tenths because you keep making it.
Yep. So the answer to this is that it will not overfill. And here's why. If you turn this into a math problem, which this is what it is, right? We're taking 1/10 of a cup, then we're adding to it 1/100th, 1/1000th, 1/10,000. We're doing that forever, right? This converted to a decimal is 0.1. And that converted to a decimal is 0.01. And that converted to a decimal is 0.001. And that converted to a decimal is 0.0001. And that's going to continue forever, right? So if I add these two together, that's 0.11. And if I add these three together, it's 0.111. If I add the next one, 0.111. If I add all of those together, I should get 0.111 forever, right? Which is exactly the number 1/9. If you do 1 divided by 9, right? How do you do 1 divided by 9? 1 divided by 9. 9 doesn't go into 1, right? So you put a decimal, you put a 0. Now you say 9 goes into 10 how many times? Once. You put a decimal here, right? Like this. Then you put a 9, subtract, you get a 1. 9 doesn't go into 1, so you carry down a 0, right? This is old school division. 9 goes in there once, 9 again. You keep doing it, you get 1. Or you just get on a calculator and do 1 divided by 9. So, not only will it not overfill, it won't even fill up halfway. It won't even fill up a third of the way. It will fill up, well, if you could do it forever, it would get to 1/9, but never past 1/9. That is counterintuitive, right? That is not what your intuition is telling you, right? Which is why we have math. This is why we have math. Because if you leave things to human, like just intuition, I mean, don't get me wrong, you always want to trust your intuition, right? But when it comes to math, the real world, trust your intuition unless you're building a bridge or building an airplane or doing something where people's lives and livelihoods matter. Then you have to have something concrete to fall back on, right? Because your intuition could be wrong, just like it was here, right? So anyways, this is what we do in Cal 2. Like, we investigate things like this in Cal 2. We're trying to figure out like these weird behaviors of things, areas underneath curves. And all right, I've gone off on a significant tangent there. Let's do our last one. I saved the best for last. X to the 4th minus 5x cubed minus 12x squared plus 36x all over x to the 3rd plus x squared. You know, I feel like I want to make a quick adaptation to the problem. Sorry, I'm going to just change one thing on the bottom. I'm going to make it x to the 4th plus x to the 3rd minus 14x squared minus 24x. All right, now there's that's an ugly one right there. We have 30 minutes. Let's see if we can do this.
Factor out an x from the top and the bottom.
Yes, but we're going to follow the steps, right? So that will be part of the steps. We're going to factor, right? We're going to do this, the numerator and denominator separately, right? So factor. Okay, when we look at the top, x to the 4th minus 5x cubed minus 12x squared plus 36x. We see the GCF we can pull out, right? X. Okay, we pull that x out. We're left with x cubed minus 5x squared minus 12x plus 36. What's in parentheses is probably going to require synthetic, right? Yeah? Okay. Now, would y'all like me to go through all the synthetic? Not really? I feel like I should, though. How about I do it? I'm not going to make the list. How about that? I mean, you could come up with the list. We're working on the number 36, right? So you could do the list. I'm just going to go right to the box in what works. Is that fair? Okay. So I go to the box. Believe 2 is going to work first. Let me just make sure I'm looking at the right thing. Yes. Okay, so I'm doing synthetic here. I've got, see, 1, -5, -12, 36. And I said 2? Yeah, 2. 2 works. So 2 goes here, we drop 1, 2 times 1 is 2, -3, -6, -18, -36. There it is, boom. Now, come back over here. Do not forget, see, students will forget that you have that x out here, right? This x is still here. And then you have x minus 2 that comes from this, right? And then these are the coefficients of what remains, which is going to be x squared minus 3x minus 18. And the x squared minus 3x minus 18 can go with synthetic, or you could just use the fact that it's quadratic and break that up. I'm going to go ahead and just do that. It's x, x minus 2, x minus 6, x plus 3. That's my numerator factored. Okay, now I'm going to do the denominator. X to the 4th plus x cubed minus 14x squared minus 24x. First step, factor out the x, right? GCF is going to go first. X cubed plus x squared minus 14x minus 24. And I've got to do synthetic again, don't I? The first number that works is -2. All right? Do I need to slow down? Am I all right? Y'all doing all right? Okay, here's what's going to work for this one. Wait, did I say -2? I did say -2.
Yeah.
Yeah, I did say -2. Okay, 1, 1, 1, 1, -14 and -24. -2 is going to work. 1 comes down. -2, -1, 2, -12, 24. Remainder is 0, or what's left is 0. Okay, come back to this. This tells me that x plus 2, right? And then this gives me x squared minus x minus 12. That's a quadratic. -4 plus 3. -4 plus 3 is what this breaks down to be. I'm not showing that step, right? Yeah, so now let's write down the function in its factored form. I'm going to go now, I'm going to rewrite this as what? X minus 2, x minus 6, x plus 3. Okay, all over this one, which was x plus 2, x minus 4, x plus 3. That is the completely factored form. I don't know, just kind of take a step back for a moment. Think about when we walked into this class first day, right? It would be pretty ambitious for us to think that we'd be able to take that and turn it into that, right, in less than 10 minutes, right? It's like if you didn't know how to do it, then we've actually made some progress here, haven't we? All right, so that's step 1. What's step 2? Holes. Do I have holes? Yes, this time I finally have holes. All right, so let's see where we have holes. Anywhere where these factors would cancel. Let me do the one that's, let me do this one first. Right here, these cancel, right? Right, so this means we have a hole where? At x equals -3. It's the place where if it's the place that makes this factor equal to 0, right? Like if I set that equal to 0 and that equals 0, I get -3. And so if I try and plug -3 into this, it's going to be undefined. That's the whole point. If I plug -3 in, I get 0 on the bottom, and division by 0 is not allowed. So our graph should not exist at -3. But it's not a vertical asymptote. Okay? Normally, whenever the bottom is 0, we have vertical asymptote, but not always. If you get 0 on the top and bottom at the same time, then you have a hole instead. What about the other thing that factors? You all saw this one, right? So when would that factor be 0? When x is what? 0. You have a hole at 0 as well. All right, from here on out in the problem, from here on out, we can completely ignore what we've canceled. Okay? We can ignore it. It's like it's not there anymore. All right? So we're really just going to be working on this piece in here. All right, step 3. X-intercepts. Okay, and I am just looking at this. X-intercepts. So where's the numerator equal to 0? 2 and 6. All right, step 4, vertical asymptotes. That's where the denominator is 0. Where's that? -2 and 4. All right, so set these two factors equal to 0, you get 2 and 6. Set these two equal to 0, you get -2 and +4. And then horizontal asymptote. Yeah, so we compare the degrees, right? We compare the degrees. 4 and 4. Ah, this is the special case. When they're equal to one another, you then have to default to the leading coefficients. And so the leading coefficient of this is 1. The leading coefficient of that is 1. So I'm going to do 1 divided by 1, which is 1. So y equals 1. 1 over 1, which is 1, is my horizontal. Time to put it all together, okay? Time to put it all together. Okay, I've got time. All right, in my picture here, see for the first time we have holes, right? I'm not going to look at the holes until the very end of the problem, the very end. After I've drawn it, I'm going to look at the holes, okay? So I'm going to do everything else like I did before. So my two x-intercepts are going to be at 2 and 6. So at 2 and 6, I have x-intercepts. And then I have verticals at -2 and 4. Horizontal asymptote of 1. So that means if I go up 1 and draw out at the edges, way out here, I've got my horizontal magnet. What now? Test points. Test points. So I've got some test points. I'm going to have a total of 5, right? Because I've got 2 x-intercepts. I've got 2 vertical asymptotes. I should have 5 test points. 1 here, -3. Can I pick 0? I can, right? Because I have a -2 here and +2 here, nothing in between, so I can pick 0. So we would find that out when? Yeah, no, this is good. You noticed it, right? I picked 0 because that was my natural thing to pick, right? But 0 is not going to work because it's a hole.
I pick different points because different.
So you're avoiding these. Okay. So do y'all see this? These holes? When I would go to plug these test points in, we're going to have a problem, aren't we? So this is something you have to pay close attention to when it comes to your holes. You've got to be aware that these points right here, you can't test them because this is where your function is undefined. So this is the one time when you have holes, this is the one time you have to pay super attention to your test points. You're not just completely free, all right? So what should we do instead of -3? We do -4. What do we do instead of 0? You would do -1? Let's do -1. I like that. And then you did +1? Yeah, I like that even better, but -1. And then between 2 and 4? 3? Between 4 and 6? 5. And then 7. There we go. So, again, you got to be careful with these, right? We can't use those. All right, you plug those in. All right, I'm just going to tell you what they are, okay? Or can I just put the points on the graph? Is that all right? And that'll tell you what they were? If you plug in -4, you're going to get a positive number. So I'm just going to put a point here. -4 goes in, and I'm plugging it into this. Plug it into this, cancel those out. Don't worry about those, all right? Just plug it in here. So -4 goes in, you get positive. If you plug in -1, you're going to get a negative. And then if you plug in 3, you're going to get a positive. And if you plug in 5, you get a negative. And if you plug in 7, you get a positive. So again, they do alternate. I haven't shown you one that doesn't, right? Maybe I'll do that on Tuesday. But I want to move on to the next section on Tuesday. But
Do we draw the lines before the holes?
I'm going to draw everything, and then when it comes to the holes, I'm just going to make a hole. All right, final picture, right? Can I go? Yeah. Okay, from this point to the left, I've got to go to the magnet. There we go, I'm going to the magnet. Be careful on this next part. When I go to the right, what? Up or down?
Oh, wait, go down.
Do we have any x-intercepts here? No, right? There's a hole, but there's not an x-intercept, right? So I'm just going to go up. Okay? Now, at -1, I'm down here. Do you all see that between here I just connect dots? That's just connecting dots. And then to the left here, I've got to go down because I have no x-intercepts. And over here, I've got to go up because I have no x-intercepts here. And then this goes like this, and then on this side connects and flattens to your horizontal. We're almost done. Last step. We need the holes. So we had a hole at 0, didn't we? So when I go to x equals 0, right here, I need a hole on the graph. So I'm going to put a hole on the graph, like that. And then the other one was at -3, wasn't it? -3 was, I don't know, somewhere over here? -3? So I'm going to go here and put a hole in my graph. Those aren't points, those are holes, right? That's the picture. So let's take a look. We're done. We're done for the day. You know what? We won't take a look. So what do I want you to do for homework? I want you to look at the review. Okay? Do you see the review has number 7 and 8? Those are both rational functions. The first one, number 7. Number 7, notice your degrees are the same. So that's one of the cases. And then on the 8, the degree of the numerator is smaller than the denominator. That's the second case. I didn't give you all 3 cases on the review. So I recommend you take a look at that. Work on that over the weekend. On Tuesday, come with questions, all right? Yes?
Are we able to get a reference sheet for this one?
Yes, we are going to do a reference sheet for this one. That's a little sheet that you can use that has your steps and procedures and all that. Yes. But we'll talk about that more on Tuesday.